headquarters are in the call. Thank you for providing us with the opportunity to bring this Tech Talks to the community. I think the idea behind it was to be able to share information as part of our knowledge management information tool, KMIT platform. Therefore, these meetings will be conducted under that umbrella and really bringing topics of interest to the community, whether it's fixatives, into method coatings, robotics, environmental remediation technologies. I think that was the purpose, the intention of the talks, to keep us engaged, to keep us the communication open, to share information, and also to store it and disseminate it via KMIT and via the talks that we're going to have. For this year, we're projecting 4 talks, or every quarter. I guess there are 3 quarters left, so 3 talks for this year. But based on the feedback, interest of the community, we hope to expand this for next year, 2021 fiscal year, in terms of 22, to do it monthly. So have a topic of interest to the community. And I think the feedback that Walter mentioned is important to that, to see what topics are of interest, and also engage the international community as we move along. So thank you for joining us. I'll go ahead and turn it over to the people that did all the work and made us look good. So Joe and our colleagues at the Savannah River National Lab, Connor, Jen, Nick, and also at FIU, Joe, Melissa, and the students, the DOE fellows that contributed toward this work. So they'll go ahead and give the presentation. So Joe, I'll turn over the floor to you.
Okay, absolutely. Thank you, Leo. Really appreciate it, and we appreciate the opportunity here. Obviously, we're starting off the Tech Talk effort here with incombustible fixatives. This has been a collaborative effort with Savannah River National Lab, primarily with Dr. Connor Nicholson. Nick Groden just joined the team, and of course, Jen as well. And then from the FIU side, to kind of elaborate and expand on Dr. Lagos's comments, also with Melissa Komanakis, Leo, and then a host of DOE fellows have participated in this over the course of the research activity for the past 3 to 4 years. Again, we're going to be discussing a novel approach to mitigating the potential release of radioisotopes under fire conditions, and specifically kind of this theme of incombustible fixatives. As we move forward, this is kind of what we're going to discuss in the agenda. First, kind of couching and giving some background on the fire risk and how that risk has impacted contingency planning across the complex. Then we're going to do a deep dive into some of the baselining we did for fixative technologies, introduce into mesh coatings as a potential solution, technological solution to this idea of incombustible fixatives, outline kind of our proof of concept. And then at that point, I'm going to turn it over to Dr. Connor Nicholson, who will describe kind of our down selection process, the code demo, the operational test and evaluation. And then we're going to finish it up with some lessons learned and really some institutional lessons learned as well, as we move forward with addressing some critical enablers to facilitate the deployment of technologies across the complex. So with that, I'll get started and kind of discuss what is the risk, what's the threat that we're looking at, and what kind of was the impetus that started this technology solution that we're facing. And really what was presented to us sometime back in 2016 timeframe was this idea of incombustible fixatives. And specifically, it originated from the Defense Nuclear Facility Safety Board, who started to conduct some fire risk analysis and kind of determined that one of the biggest, if not the dominant source of risk to workers in the public across the DOE EM complex deals with fire. And you can see that they've kind of highlighted that for a variety of both internal risk factors that could promote fire conditions, everything from degraded facilities and the electrical wiring being quite decrepit, to lack of viable fire barriers with qualified fire ratings, to some more of the external risk factors, seismic induced fires and natural disasters. So what we kind of encountered quickly was this idea that fire is a very prevalent risk. And once that was promulgated throughout the DOE EM complex, it promoted this need for some complex-wide contingency planning and to conduct an analysis of what could a fire and or seismic induced fire cause across each of the individual facilities that are undergoing D&D type activities across the entire complex. And as you see, those types of incidents and the frequencies are kind of summarized in this one slide here, from building 440 all the way to what we were specifically kind of targeting with the SRS 235F pump facility. And in every instance across the complex, this idea of the risk or threat of fire and what the potential impact down to some pretty specific details has been highlighted and outlined in those fire events column. When you go across with the SRS 235F building, you can see the particular scenarios that are identified there to include a potential full facility fire that has been induced through some type of seismic activity. So this is not just a problem as highlighted by the DNFSB, et cetera, for the SRS 235F facility, but fire across the complex is a very big risk factor as you look across. And so this impacted the basis for interim operations. It was incorporated and integrated into the SRS 235F facility that kind of did an assessment and evaluation of the potential consequences of what a seismically induced full facility fire could pose in terms of threat both to the environment as well as to the co-located worker. And you can see it's pretty substantial as you review that. And then how those fires could be induced, as we've already kind of highlighted. But then from this came the potential idea and requirement to move forward and develop a fire resilient or a fire retardant, or in essence, an incombustible fixative, some type of technology that could be utilized to immobilize and or fix residual contamination inside of a facility being decommissioned, and then have that maintain a level of fire resilience even when exposed to some of these threats, and mitigate the release of those radioisotopes under fire or thermal conditions. So as we started from the FIU side, the Applied Research Center, our initial task was to kind of gauge and get a sense of where are we today when it comes to fixatives. At this particular time, it was in about, as stated, 2016, and we went across and conducted an extensive baseline of 5 industry fixatives and strippable coatings that were being utilized fairly extensively across the DOE EM complex. And we tested those particular fixatives and baselined them in a series of experiments that, number one, exposed them and introduced them to thermal stressors coming from both an open flame, i.e. an open fire, and then we also explored and baselined them against kind of an incremental temperature increase utilizing a muffle furnace. We put them on a variety of substrates as we went through and tested these particular fixatives and baselined them from stainless steel, wood, glass, sheetrock, etc. And then we went through and collected data on the combustibility, mass loss, impacts on adhesion, its transport, and of course its chemical breakdown as well. So the first part of this was, where are we? What, how much of a vulnerability with the existing fixatives being used across the complex, do we really have when it comes to a fire threat? And what we found is that the current state of fixative technology is that we got a resounding fail from our assessment and collaboration with Savannah River National Lab. And we kind of depict here in this particular slide what we kind of call your basic fixative technology profile. And what does it look like under various temperatures over various periods of time and mass loss? And so to kind of walk you through this, if you look on the far left of the slide, we kind of have a fixative that we put completely intact. And then as soon as we started to expose it to temperatures as low as 250 to 300 degrees, we began to observe some pretty significant contaminant transport problems that began. Specifically, the fixative started to melt. And then as you move across the spectrum and incrementally increase those temperatures, you can see we have a saying in the Marine Corps, nothing good ever happens past midnight when you're on liberty. In the fixative world, once you hit 700 degrees, nothing good happens. It becomes literally a shell of itself. And you can see by the time we hit those temperatures, we have across the board, and we'll go into this individually, significant mass loss, discoloration, desiccation, cracking, and flaking of the fixative and or strippable coating, somewhere upwards of anywhere from 75 to 90% mass loss after being exposed to temperatures around 700 degrees for a short span of time. And so what we kind of noticed is that we have a pretty significant vulnerability when it comes to the existing kind of portfolio of fixative technologies currently being used across the DOE EM complex. And here's what we're talking about. We use glow germ to kind of simulate the contaminant. Again, we utilize this in every one of the fixatives that we outline for the 5 fixatives, and you can kind of see how the contaminant transports or is transported at pretty relatively low temperatures, in this case about 250 degrees. And it just got worse, obviously, as we moved forward and increased the temperature. And this is kind of what we, at various junctures, as we increased the temperature and took it out and conducted some just baseline analysis. And so for each of the 5 fixatives, we've kind of broken it down here, and you can see where discoloration and expansion occurred as low as 400 in this particular case. Discoloration, bubbling, off-gassing started to get pretty significant at temperatures around 600. And then, of course, 75 to 90% of the mass loss occurred at temperatures of 800 degrees. To kind of put the 800 degrees in perspective, a basic wood fire or bonfire temperatures rise or get to approximately 1100 to 1200 degrees. So we're significantly lower than that when we started to have total failure of what we've kind of classified as total failure of the existing fixatives in the DO that are currently being utilized across the complex. And so this is fixative A. We kind of use the naming convention for each of these. Connor will go into greater detail because Savannah River National Lab did a very good evaluation of and baselining of these fixatives in environmental conditions of high heat, humidity, water absorption, and of course radiological hardening, rad hardening as well. So for fixative B, you can see same type of efforts that or same almost type of characterization at each of the various temperatures that we introduced and exposed it to. Fixative C, the strippable coating that we evaluated as well. And then, of course, the last baseline fixative that we did right here. So the bottom line, what we quickly ascertained is that the current fixatives being utilized across the complex were not very fire resilient. They were not meeting this requirement for incombustible fixatives that was kind of being outlined there in the research activity, and that we needed a better solution to meet this, given the threat of fire across the entire complex for D&D and storage activities. And so we kind of stepped out and conducted some literature search, baseline, basic research, but really based on prior experience in the military when we were in Afghanistan and Iraq, something that we would use extensively in terms of kind of hardening our facilities with a passive fire retardant, were these things called intumescent coatings. And we would put them on critical infrastructure, paint a coating on, roll it on, and it would provide a level of fire protection against rocket attacks, etc. And as we kind of dug into this, the initial idea was that perhaps we could improve the operational performance of the current fixatives being used extensively across the complex, and we could enhance their overall operational performance when exposed to thermal stressors by simply layering an intumescent coating over the fixative. So in other words, you would place the fixative, and then over top of that fixative, you would put an intumescent coating, and that intumescent coating would in essence protect the layer of the fixative underneath it, and therefore you could maintain and continue to fix and immobilize residual contamination even when exposed to fire conditions. And like I said, that was the concept of using something that was being prevalently used in the U.S. military from my experience in Afghanistan and Iraq. Then as we conducted additional research, NASA uses intumescent coatings extensively, oil and gas industry, and a host of other industries utilize these passive polymers coatings to passive fire protection coatings for that particular effort. And so we conducted kind of a series of proof of concept experiments. You can see here are some of the characteristics that are associated with these intumescent coatings and the level of protection that they provide when you have them and when you don't. And the picture to the right kind of shows you an example of how well they can protect certain structures, certain infrastructure, when you have these passive fire protection coatings on them. They have been rigorously tested to a set of fire standards from ASTM, NFPA, UL, and a host of others, up to 2,000 degrees Fahrenheit and for durations of up to 2 hours. They're very cost effective, with some of these intumescent coatings being as low as about $2.75 per square foot when you look at it across and you buy them. And as Connor and his team will show, they also prove to be quite radiation resilient and very good in extreme environmental conditions, high heat and humidity. And really, one of the long poles in a tent as well is how easily they can be applied and utilized using tools that are relatively common on approved tooling lists in several of the facilities undergoing decommissioning, i.e. can they be utilized and applied using brush, roller sprayers, or a host of other techniques that are relatively easy to utilize and again have been approved on the tooling list. So we conducted a host of proof of concept experiments here at FIU, specifically focused on the layering idea. This really kind of originated with Mike Serrato out at Savannah River National Lab, that maybe you could bring these intumescent coatings, perhaps layer them on top of these existing fixatives, and you could add a level of operational enhancement. and then of course Aaron, Washington, and Connor as well. And so as we went through and did that, in every instance, all 5 of the fixatives, when layered with these intumescent coatings, conclusively displayed an improvement in their overall enhanced fire resiliency. And we were exposing these, as you can see, to propane torches. Those temperatures exceeded well over 2,000 degrees. And in every instance, the intumescent coating, once it charred, it got up to 50 to 100 times its size and expanded. It did an excellent job at providing a level of thermal insulation and protection on all of the fixatives, existing fixatives that were underneath it, and in every single substrate, whether that substrate was wood, stainless steel, glass, sheetrock, whatever it might be. It did very good at minimizing the flame spread as well, and then of course afforded some long-term thermal protection. In this particular case, up to 35 plus minutes of pretty direct heat and fire exposure, minimized the smoke, and it was exceptionally, as we determined, easy to apply. We'll show you a video of the picture there that kind of shows it, but the one on the left and the right are 2 fixatives that are commonly used. The one on the left is the fixative A, and the one on the right is fixative B. And then, of course, the one in the middle is fixative B with a layer of intumescent coating. And you'll see in the video that comes up just the additional level of fire protection that is afforded through this layering concept by applying an intumescent coating on it. And then, of course, the picture beneath it right here, once we did this after 35 minutes and we took away the char that was provided by the intumescent coating, you can see that the fixative underneath it was relatively intact. And so here's kind of the video, like I said, as we move forward. And so it's at this juncture when we, at the end of our proof of concept and the potential utility of intumescent coatings and a layering concept, we thought we might be able to truly address the vulnerability of the fixatives being utilized across the complex by adding these intumescent coatings. So we saw some potential game-changing results. But at that time, we had the introduction, and Dr. Connor Nicholson shows up, and he had an interesting idea. And so I'm going to turn it over to Connor, and you have it from here. Just let me know when you want to turn the slide. Go.
Sounds good. So anyone that is familiar with DOE knows that we absolutely hate being in an area that has any potential hazards longer than we need to be. And so as Joe and I were going through this process back and forth, both from DOE and SRNL's perspective, we never really found a very good set of standards or metrics or anything of that nature that really drew a box around what a fixative was supposed to be. What is it supposed to live up to? And so, I just asked the question, so why are we going with this layering approach? Anyone that has dealt with multiple coats of paints or had to change types of paints know that there can be pretty bad incompatibilities. And that's on top of increasing worker exposure in a radiation area, along with other hazards. If you can get away with one coating versus multiple, that's obviously going to be the way you want to go. One of the other drivers for this was that our test bed scenario, 235F, has it was an old production facility for plutonium-238, which is very mobile in the environment due to an alpha recoil. It likes to aerate itself. And so the intumescing action that Joe discussed that has a fluffing layer on top of it was not seen as a huge win for them, because the concern was that charring layer will be consumed throughout any fire event, and you'll still get aeration of your contamination. And what they asked was really if we could have something that could bake into a very hard, almost ceramic-like material, that would be the most ideal. So Joe, if you would jump into the next slide, please. And so this is really the big overview of both efforts. In asking that key question as we were moving through this, what does the fixative need to live up to? What does it need to do? And how do we benchmark it? No one had a good answer. So Joe and I decided to go ahead and outline a number of key parameters that seemed important, at least to us, and would help us better make the argument in facility space as well as DSA space. So the items that we came up with were environmental. Obviously, you want to make sure that temperature and humidity on these old buildings that are not well climate controlled are going to stand up to what they're going to go through. Radiological, it's going to affix radiological contamination. So if that's going to cause embrittlement or anything like that, that's going to down select it. Adhesion, we want to make sure that it's going to stay adhered to that substrate, because bottom line here is you want to adhere any contamination that you have on those surfaces. Obviously, the fire performance that Joe has already gone through, we want to make sure that it can stand up and we can potentially credit these platforms. And finally, mass loss, we want to make sure there's enough after a fire event occurs that we can still claim that what was fixed is still fixed with as high of confidence as we can have. And so this has undergone a lot of field testing. You can kind of see the timeline there at the bottom. But let's go ahead and jump to the slide, Joe. So we did a number of tests, 7 different fixatives and strippable coatings. And from Savannah River's end, we wanted to make sure that this was as compatible on various materials that we would find in a facility. It would be as compatible as possible. So we chose sheet metal. Everyone's very familiar with sheet metal in their facilities. But wood and sheetrock, which stems from anyone that knows Mike Serrato knows that he likes to get himself into the weird facilities. And that was driven by, I believe, a Canadian need at the time. They had a lot of contaminated wood in their structures. So we wanted to make sure that whatever we were doing, specifically from SRNL's end related to environmental testing, was applicable across the board, or at least informed the end users of what to expect. So these were prepared at FIU and shipped to us. And as they were received, it was important to note that we already had delamination of DG and a couple of the other fixatives as well. AS did not stand up at all. As we pulled it out of the package, we had a nice clean piece of wood or stainless steel. And then CC also delaminated pretty severely, specifically from the steel, but there were also bubbles that were noted from the transit. Next slide. In testing our water response, you have a full facility fire. The thought here was sprinklers are going to go off, so that thing's going to be sitting in water at least for a while. So we want to make sure that during that event, anything that either sees fire or doesn't see fire is still going to be able to stand up. And what we found was, as we were moving through the fixatives that are used widely across the complex, a lot of them really soaked up a lot of water, or they dissolved completely. FG was one of our other intumescent materials. I believe it was the one that intumesced that Joe was just talking about, and it was found to dissolve as well. But FD that we were moving through showed no response to water after 4 hours or even up to 24 hours of soaking, at which point we declared it effectively stable when submerged. Go ahead, next slide. In considering environmental response, we wanted to, because these facilities can sit cold and dark, they can lose their temperature controls. You might lose your chiller, as happened to us in 235F, which we'll get to later on. You never know what this stuff is going to see. So we wanted to make sure that it could deal with high temperature, low temperature, high humidity as we get in at Savannah River, and low humidity as you might get in some of our drier climates. And Next slide, Joe. What we found here was also pretty telling in terms of what the expected performance would be. A lot of your traditional fixatives, which would be your ABC, your PBS, and CC, swole, or they took up that water, or they delaminated. CC, we say here it proved stable at all conditions, but during cure testing, actually, we found that if it was already post-cured in a nominal environment, then it was stable. But if you lost control of your climate while it was still curing, it would actually delaminate fairly significantly, both from stainless steel and from wood. DG was our strippable coating, and it absorbed the most water. It basically dissolved off, which made sense because it is meant to be soluble. But our two intumescent coatings here, just from environmental stimulus, proved stable at all conditions. That'd be our FG and our FD. Next slide. I didn't go into it here because there wasn't a lot to see, but from the radiological perspective, everything held up to a 5 rad top. We figured was a good enough dose threshold for something that has already underwent gross decon. And that's kind of what the limitations on our testing scenario were going to be in 235F. So as we move through this, we did a lot of the front end data bounding, and we found that FD was the one to move forward with. As Joe said, the tooling and the application are the most important parts here. So this was initially performed at FIU to identify a lot of the issues in application from the operator's end. And initially, these things are effectively paint. And so your first thought is, let's just go ahead and roll it on there. It'll all be fine, and we'll just keep layering successive coatings on there. Now it's found to take pretty much forever. Because this material in particular, and Joe, correct me if I'm wrong, needed to achieve something along the lines of 1/8 of an inch thickness to meet its various ASTM and other ratings for fire tolerance. So when we moved into this, we have a cold mock-up of one of the cells we were going to perform this in. And this really helped us learn a lot about what we were going to expect when we got in the facility. We had our operators that would be doing the work go in to do both a vertical application on the walls as well as a horizontal application on the floor in areas that we knew were contaminated, but were still going to be working areas after this material was applied, and we wanted to see how the material held up. From a cold testing perspective, we learned a lot about how whichever worker is going to be performing the task can have a lot of variability in application thicknesses over the body of what is applied. We also learned that if we applied too much at one time, which you could see in that first picture on the left, the bottom portion of the material would dry first, and the wet portion in the middle would completely slough off and fall off on the floor. So we had to make allowances to, even though we were only applying one material, we needed to give this material enough time to cure so that it wouldn't sag under its own weight. We also found that curing in a stagnant closed system, which this representative hot cell was, it will not cure. You have to have ventilation, which you would anticipate on a real hot cell. But here we had no air circulating on it. So your ventilation plays a much larger effect than you might think. In terms of gauging your thickness, making sure that you get up to where you need to be, our gauge could give low results if the backing was not metal. All application was anticipated to be metal here, but as you can see in that final picture there at the bottom right, we didn't have a piece of metal on the back of it initially. And we knew from a caliper reading that it was nice and thick. It was what we needed, but it was not giving us what we needed. So testing and verifying your equipment on the front end is very important. And finally, in terms of limiting worker time in there, if it had been a painting operation where they had to go in and really roll everything onto the walls, this would have taken days worth of labor. But to get an entire quart of material on the wall was a minute and a half. And in our applications we'll go through here in the next few slides, I believe we did something like 3 to 4 quarts, depending on the area that we were applying it to in a given day. So real operator time in the gloves, once we started the application, was on the order of 10 minutes to get this stuff on the wall and fixate that contamination. Next slide. So there were 2 areas that we applied this to. One of them was an entry hood, which you can see on the left, and the other was one of our hot cells that the cold demonstration hot cell was modeled after. And there was a lot of preparation we had to do to make sure that this kind of met what our intentions were. We wanted to make sure that these were gross econ. We also wanted to make sure that the workers, the operators and the facility owners were going through everything that they would consider during closure for these types of deals, both from a protection standpoint, which would be the flex wall there, as well as if you're still going to be performing operations in these areas, what key infrastructure do we need to protect? So on the entry hood on the left, we installed a flex wall to kind of give a protection so that any overspray didn't come back on the operators who were dressed out in 2 pair. We cleared out all the debris in the hood since we're going to be applying to both the back wall as well as the floor. And then the facility side said, you know, there's a square door in the back, which you can't really see from this picture, that we'd really like to maintain functionality of. So what we did was we masked it with a lot of plastic, and you'll see the impacts of that later on, to make sure that we could go back in and restore use of that door. Likewise, in our hot cell, we had to install an electrical pass-through in one of the gloves, which is number 1 there. This cell did not have power. So we had to power our sprayer. We had to power the other tertiary stuff that was going on. We had to shield the electrical pass-through because they said, hey, we don't want to get a ton of stuff on this because we don't know how it will react, but we want to make sure that electrical pass-through could come out as safe and clean as possible. So we put another sheet of plastic over it, taped it up, and that worked well. We wanted to protect the transfer between cell 7 and cell 8. And here we just hung a piece of cardboard over it. We were going to go with a piece of sheet metal that could be removed later on, but we found that it was actually going to be too heavy for our workers in those gloves on the back end to hang on that door. Clear out the debris, obviously, and then we had to bring in all of our equipment, which was the sprayer, preloaded cartridges, both with the fixative material and water, to make sure that the sprayer was able to hold up over multiple applications if we needed, and other necessary equipment such as the thickness gauge and things of that nature. Next slide. In the entry hood, we were able to have 2 guys in the flex wall at a time, and one guy would spray out his bottle, swap another bottle in, hand it off to the other worker, and just keep it going. It was about a 15-minute evolution all in. They did find, in terms of keeping it fairly even across the way, it was actually half a bottle. I apologize. Half a bottle in one position, hand it off, spray it on, and then they would have to monitor out of the gloves, bring another bottle in, because we were trying to keep the area as clean as possible, and keep going. And what we found in our thickness measurements there at the bottom was a midline for those workers was very hard to establish. You can see there's a region just to the right of the midline that is significantly thicker than anywhere else. And due to the sloughing issue, we did do this in 2 evolutions, which worked out well. But our target here was 3.2 millimeters, which is how our device read it off. And in total for this, let's see, what is that? 5.5 feet by nearly 3 feet area, we put just over 1.5 gallons on the wall. Next slide, Joe. It was very similar for the hot cell. I abbreviated this just because it's effectively the same process. You can see the befores and after here. The red material is obviously what we're putting on the walls. We were able to get very uniform, very up to spec thickness on both the walls in each of the areas. Go ahead, Joe. Next slide. For the floor, we went with a different application method that FIU developed. Effectively poured on the floor and spread it around. There's no reason to reinvent any wheel or come up with something fancy when just pouring it on will do well enough. And you can see from the thicknesses here, we were able to achieve everything we needed to. I believe we had to go back in one area in the back left and reapply just a little bit more because there was some equipment that was welded to the floor. But other than that, just over a gallon was placed on the floor in one spread period, and then we did touch-ups after that. That was where we needed to be. Next slide. And so I somewhat facetiously put up the entry hood slide since we couldn't see it from the window where we were at. But you can see in process L7, everything went well, everything went smoothly, and we got a nice coating on the floor. Next slide. Some of the lessons learned, just to the left of that entry hood was a cam that was monitoring for any airborne contamination, and we were fully prepared to set that thing off for our operations in the hood. But the flex wall worked very well in terms of containing that contamination. It was also important, going back to that cold demo, our operators had trained enough with this to get a gut feeling when it was potentially getting too thick or wasn't thick enough. So having that training prior to going into the facility was very important. In terms of cell 7, the masking for the electrical pass-through needed to be rethought. You can see how the plastic was bowing out and it actually got in the way of the coating. So one thought that came up was suction cups rather than attempting to duct tape it. Things of that nature might be a way forward. And one of the other issues we ran into, everyone thought they were on the same page, but our sprayer went in with the nozzle rotated by 90 degrees. So we got to introduce sharps in the form of Allen wrenches to change the orientation of the nozzle while in the hot cell, rather than outside where it would have been much easier. Next slide. A couple of others, and I won't go into all of these, but our initial cure time in the mock-up was roughly 24 hours. Importantly, when we would go in the next day, it was found to still be wet, especially in the entry hood. And so we had to call a timeout, give it another day or so for it to dry. And this was driven by the fact that we lost our chiller and our environmental air conditioning multiple times over this application demo. And that had a real big effect because this material uses water as its solvent. So if you've got lots of water in the air and you're not moving air through the facility, the water's not going to come out and it's not going to cure. On cell 7, one of the biggest concerns that they had was that residual fire dam would get on the gloves, would dry, would potentially lead to a puncture just from embrittlement. None of that happened. We got plenty of fire dam all over those gloves, and they held up for, I believe, 3 weeks through the entire evolution of this activity. And then they just threw in new gloves because they knew that they weren't going to be working in there for a while, but they wanted new gloves when they did go back in. And also, in terms of the cells, we thought this through after the fact, but coating the floor first probably would have been the better method because majority of the contamination was actually found to be on the floor. And through spraying activities, you're going to stir some of that up. Next slide, Joe. So how did we hold up? Which is the question that everyone, I'm sure, is asking themselves. Initial application was in late 2018. We just went back in last month to see how things were going. We were not able to go into cell 7 because it has officially been closed out and we're not able to get hands and gloves in that hot cell. But you could see it from the shift operations base. So you'll see some pictures there and I've got some comments about his performance. Entry hood, the glove wall had been removed. The plastic cover over the square door that we wanted to maintain had also been removed. And you'll see some depressions on the floor where we were having to store some stuff internal that caused some sagging. That also was removed. So all we've got left as we go through these will be pictures of the actual material that was applied. Next slide. So first, the entry hood. You know, the operators went in and they took a peek. It was their first time looking at it in 2 years, and they came up to the window and to the clean area, and the operator yelled loudly so that I could hear him. It looks like crap, and you know, your heart sinks. But when you look at these, you'll see there's a lot of reasoning as to why. The wall conditions, again, we cut out that plastic coating. You can see the square door on the right side of that top picture. It still has full functionality. You also see a nice uniform fixative coating to the left of that, which was area that had no masking over it or anything like that. There was a circular door on the opposite side of this picture that wasn't pictured that maintained just as good cohesion as this material did, because it had no masking on it whatsoever. You'll also see from our thickness measurements, and again, remember this is 2 years on, almost exactly. Anywhere that the plastic was not masking the door, we still maintained our 3 millimeters for the most parts. Your corners obviously get a little bit thin, which we can attribute to operators not spraying high enough, as well as you can see in that top picture there's some running marks. As it continues to cure over about a month life period, it will run just a little bit. So reapplication may be necessary depending on how you bound, how much you trust this material and what thickness. The interior points, again, were effectively non-existent due to that plastic removal. But you can see in the picture just above the door, we did retain some of the fire dam. It's just peeking out of that top right corner. We did retain some fire dam on top of the door. So we got decent thicknesses there. Next slide, Joe. For the wall, and we'll get a better picture here soon enough, our thicknesses were really knocking it out of the park everywhere, except you can see that middle point in the back. That was due to the plastic delamination again for protecting the door. You can see how there's a little bit of area that isn't coated underneath that square door. We did notice depressions in the material, which is almost directly in front of that square door, and not pictured here, but we'll see it in a minute, is a significant amount of cracking underneath the round door. Storage of our equipment was not considered. We thought that, you know, once it's cured, it's cured after 48 hours. But it turns out the material still stays a little bit soft. It needs a little longer to truly harden up. So setting equipment on it could have overcome some of the depressions that we'll see. We really want to make sure that surface remains as clean as possible for about a month. Next slide. For the hot cells, you see all this white powder. That is desiccant. I mentioned we had to run water through our sprayer to ensure that it didn't clog. That is the desiccant that got blown out of the containment. We weren't able to get thickness measurements, as I said, and we did notice the same cracking that we saw in the entry hood. The area under the single glove port where our pass-through was, though, had no running or cracking or depressions. It was kept completely clear of all activities since we were using only the dual glove ports. And the wall also had a visual appearance, although it was very hard to get a picture, that it was still uniform and there were no issues at all. Next slide. So many of you are thinking, great, well, but what about the cracking? What about the depressions? As I said, the sprayer has to be cleaned for multiple spray activities. So what we had was desiccant inside a plastic bag. The operators would require two men to hold it. They'd attempt to bind the collar of the bag around the sprayer and then spray an entire quart of water through. Unfortunately, when you're in 2 pair plus an additional glove for whatever confinement you have, sometimes you get spills, sometimes you get a little blowback for air going in. And where you see the cracking most, especially in that top picture, you notice it is the desiccant that is all in those cracks. And this makes a lot of sense. One of the other reasons that we really liked this candidate for an intumescent material was it does use water as its solvent. It's not going to have a volatile component. So we want to make sure that it remains as clear as possible. But if you have something that absorbs water, it's going to crack. And we also noted these cracks in the hot cell as well, though again it was hard to get a picture of. But it was only underneath those dual gloves where we dropped an entire bag of desiccant on the floor, which was why those previous pictures had so much on the floor. Next slide. So here I'll hand it off to Joe. This was the technical piece, and as there's a lot to be taken away, both from the technical side as well as from the regulatory side, both within DOE and in the international community. So, Joe, over to you.
Super, thanks. And we're going to hit just a few more slides, but bottom line is what Connor covered there obviously was the down selection process through his idea of a standalone bisolayering concept. The FD intumescent coating proved to be the selection of choice for all the various reasons articulated. And with the modifications, as he outlined through the lessons learned, what I kind of call the tactical lessons learned and application, etc., we may have identified a more fire-resistant standalone fixative that has the capacity to be able to address and mitigate the potential release of residual contamination, even when exposed to thermal conditions. For sure, we feel we have identified a technology that provides an increased operational performance over the existing line of fixatives that are currently used extensively across the DOE EM complex. Most importantly, this is a commercial off-the-shelf technology, and so there were no adaptations and or modifications to it as we went forward and applied it. Now, Connor kind of addressed in good detail the tactical lessons learned with the technology itself. But as we moved and went through this particular activity, and he touched upon it there at the beginning, we did identify some pretty important critical enablers and institutional barriers that should be addressed as well in any type of technology deployment. And since we're talking tech talks here, and this will be a common theme throughout, we found that more often than not, it's not just about the performance of the technology itself. Very often you can get that to work, but you have to address and take a holistic approach to technology deployment, which addresses the regulatory issues, the standards issues, and the institutional barrier issues. Otherwise, that fantastic technological solution is simply not going to transition into, in this particular case, a hot demo, for example. And so with that, I'll cover a couple that we kind of found, and Connor did a good job of identifying this. When we started out, we noticed quickly that there were no definitive standard specifications related to fixative technologies across the complex. And so no matter, even though these types of technologies in various forms have been utilized for quite some time, specifically what we want them to do and to what standard we want them to perform had not been identified in any formal fashion. And so we found quickly that there seemed to be, as we discussed with the safety personnel at the facility, the fire personnel, the project managers, et cetera, that they were assuming potentially a tremendous risk in moving this into an operational test and evaluation, a hot demo, and that we needed to come up with a more methodical process to mitigate the risk to the end user for them to facilitate its transition in test and evaluation and really utilization as we move forward. And so we kind of heard that and we were kind of, well, what's the role of international consensus-based standards? Could they potentially play a role in addressing and mitigating that risk and kind of giving that stamp of approval? And so over the course of 2 years at Waste Management and other forums, we developed a very simplistic yet effective survey of about 222 folks and kind of posed 2 scenarios to them with 2 particular questions. If you had a choice between technology 1 and technology 2, 2 identical technologies, except technology 2 had been certified and underwent a series of stamps or safety inspections, so to speak, that met this core group of consensus-based, agreed upon standards that were independently tested. Which one would you take if you had 2 absolutely identical technologies? And without fail, as you can see in the blue, all 222 respondents obviously said, of course, we would take technology 2 over technology 1 because it has that added level of assurance that it met some consensus-based, approved upon, independently tested standards. And then we took that a step further and said, okay, well, what if between those 2 particular exact same technologies, with the only difference being the cost per square foot, so basically the cost, would you still choose technology 2 over technology 1? And of course, in most instances, we had a few cheapskates. I joke about that, 6, but the overwhelming response once again indicated that the role of standards, the role of these international standards, and number 1, identifying specifically what you want the technology to be able to do, in this case, fixative technologies, and then a set of uniform testing protocols by which you can test to ensure that they do what you say they are going to do, so you can compare apples with apples independently, really made a significant difference in the ability of a technology. It served as a critical enabler for that technology to transition into the hot demo phase and ultimately for diffusion of that technology across the board. And so when we kind of introduced that and showed Andy at the time, the director of DOE EM's Office of Infrastructure and D&D, recently retired, and we showed that to him. He said, he bit off on this particular idea that the role of these consensus-based international standards organizations could really come in here and not just facilitate the diffusion of technologies in terms of fixatives, but perhaps this is a model that we could go forward with across multiple technologies that are utilized for decommissioning. And so here's kind of, so Connor and I, Aaron Washington, a few others, Rick Dimmer out at Idaho National Lab, who were dealing quite extensively with fixative technologies, ended up going to ASTM International, and we kind of looked and we found the E1003 subcommittee as a subcommittee that deals and focuses primarily on D&D technologies and the development of standards and the development of testing protocols for those technologies, for example, fixatives. And we kind of went in there, and between myself, I'm the chairman of that particular subcommittee now. Connor, who you just heard, is the vice chairman. And we kind of shifted based off of the request of Andy and DOE EM and we took on this task of moving forward and developing ASTM standards for fixative technologies. And we started with, what is it we want the fixative to do? What is that explicit set of requirements that need to be satisfied? In my old terminology from my old job, what are the mil specs that you want this thing to do? And then we needed to start looking at, okay, now that we've defined what it is we want, what is that definitive procedure, that uniform testing protocol that can be utilized to make sure it meets that requisite standard, whether that's in the realm of thermal stressors and fire, adhesion under a variety of conditions, how should the fixative perform under environmental conditions, into what temperature and humidity, et cetera, et cetera. And so as we went, we started and we defined, for example, strippable and removable coatings. We defined what the specific standard specifications for permanent coating should be. We went through that standards development process and actually promulgated several standards that are now being utilized and promulgated across the community, the D&D community, for what we expect a fixative technology to be able to do. And it's a little outdated, but we now actually have 2 standard practices, which are really kind of testing protocols for how you go through and measure and evaluate decontamination techniques. Rick Dimmer played a significant role in that. And then another one that he played a role in, and of course Connor took the lead on a couple for expanding the idea of fixatives to 3D fixatives. That's a different tech talk, but utilization of foams, and we kind of took this model and defined what we wanted to do first, and then kind of build to it from that point. But the bottom line is the role of standards and the strategic integration of international consensus-based standards can truly may be a game changer and is a critical enabler to facilitating the transition of technologies from lab to market, whether in an operational test and evaluation, hot demo, and ultimately in mainstream utilization and diffusion of that technology across the complex. And then the second big takeaway that we took as we went with this, when we were talking to the site personnel, they said, this is fantastic, but it would really be great if we were able to take credit for the positive impacts that these types of technologies such as fixatives make in terms of reducing the material at risk, for example. And as we did that, Connor and I, and we've really brought Melissa on board as well, who's kind of utilizing this effort to as the basis of her graduate work, PhD, et cetera. We noticed that the guiding document for this technology, fixative technologies, DOE Handbook 3010, which really contains the methodology for the source term formula and others, and serves as a foundation as well for safety basis calculations, computer modeling programs, et cetera. It hadn't been updated since 1994. And so what it created, as I'll show you in the next slide, is it kind of outlines these various states that a contaminant can be in, anywhere from powder, et cetera. But it did not really take into consideration what that contaminant would look like if you added a polymer fixative to it, or a fixative, you know, that came in there and it changed what we kind of called a change of state from powder to kind of the solid polymer. And so in other words, we know intuitively, kind of as Andy said, Connor and ourselves, we know that fixatives are going to provide a positive impact on airborne release fractions and respirable fractions under a variety of conditions and stressors. But since the handbook had not been updated since 1994, it did not account for these types of technologies, and therefore the material at risk was carried at a higher level with them, even when you used them. And so what we kind of are moving forward with now, thanks to DOE EM, and they've kind of identified this and concur that this is an area that if you're going to really move forward with this holistic technology development approach, and you're not just going to identify FD intumescent coating as a technological solution, but we also need to move out and address some of these other external critical enablers and institutional barriers, move forward with the standards, as we said. And then they said, let's move forward and start to get and build the empirical data necessary to confirm that fixative technologies do in fact have positive impacts on airborne release fractions and respirable fractions, that it does in fact create kind of this change of state from powder to something else, and that something else polymer state should be accounted for in the update of the handbook, because it's going to impact those airborne release fraction and respirable fraction coefficients. And you could thereby really incentivize and take credit for the reduction in the material at risk, the reduction of the source term, by simply updating the handbook. And so this effort is being undertaken right now with, like I said, ourselves, Connor, Savannah River National Lab, others, and of course, Melissa on our team here is utilizing it kind of as the basis of her graduate studies and PhD. So we hope at the end of this, in the next 1 to 2 years, we'll be able to provide the data necessary to show the positive impacts of those fixative technologies. Then they could be incorporated into the next update of the DOE handbook, and then you meet what the site personnel had requested, and you can not only mitigate their risk by using the standard side of the house, so you address one human factor through standards, which we're moving forward with, but then you can also incentivize them to utilize the technology by updating the DOE handbook. And so with that, I think that we'll turn it over for any questions and answers. We really appreciate the opportunity to present this first kind of in the series of Tech Talks. And with that, I'll turn it over to Leo and Walter to kind of address it, or to the crowd for any questions from myself or Connor.
Yes, so thank you, Joe, and thank you to the presenter. So right now, if there's any questions, I guess we have the mic open for Joe, Connor. We would like to entertain any questions you may have. I know we went over the hour. Our apologies, but such an interesting topic. So, anyways, if there's no questions, I just wanted to remind you of the feedback form. You see it right there on the screen. I think JP also sent the link to the Tech Talks and the presentation. You can find that in KMIT as well. And also, well, let me, before I jump to the next thing, I wanted to thank the presenters, of course. I think this has been a great collaboration between Savannah River National Lab and FIU. So Connor and Joe, thank you for the leadership. I think Connie Herman on the line, and Jennifer, Nick, and Connor, and I have to put the plug here. Our own Tristan Simo Esponce is on the line as well, now working at Savannah River National Lab. And I want to thank the our sponsors, right? The DOE Department of Energy, Office of Environmental Management. Without their support, this would not be possible. So thank you. Those individuals that are on the line right now, Jania, JP, Jennifer, thank you for your support. Just wanted to point out the next talk, I guess, is scheduled for April 20th. The topic will be robotics. So we have named that talk Use of Robotics in Nuclear Decommissioning Applications. And that will have a similar presentation with collaborations between FIU and other institutions, across the DOE complex, as also international partners as well. So we'll look forward to that. So let me open the floor one more time before we leave, and see if there's any comments, questions. Jania, I see you on the line. I'm not sure if you wanted to say a few words. I think I put you on the spot, Jania.
And while Jania is coming on the line, Leo, I might just say that, again, there will be a detailed final report that is being developed right now. Nick from Savannah River National Lab is kind of leading the overall consolidation of all of the data that you've seen over the past 5 years. FIU and Savannah River National Lab are contributing to that. And we expect that the final report for this particular activity is a deliverable that we're kind of providing to DOE EM, and will obviously be published via OSTI and a variety, KMIT, and a variety of other knowledge management tools to get the information out there. So you kind of got a precursor snapshot in a brief form here, but a much more detailed, robust effort will be produced here over the next, I think it's released it here, the deliverable sometime in March. Jen and Nick can kind of confirm that. But between us, we're working diligently with our collaborator there at Savannah River National Lab to get that report out to DOE, EM, Jania, JP, and others. And so with that, Jania should be on the line and have time to find her mute button.
She's having issues with her microphone, but she did send a text on the chat. So thank you, Jania. So Jennifer or JP, if you would like to say a few words, just let us know before we depart.
This is Jennifer. This is wonderful. Is it possible?
I think you're cutting off, Jennifer. I'm sorry.
I'm sorry. Is it possible to add a copy of the slide deck?
I wasn't able to capture that. My apologies, Jennifer. I think the microphone may not be working.
Jennifer, this is Walter. You might be connected with two devices. That's why we're getting an echo. So if you can mute one device, and you should be able to hear it.
Oh, in the meantime, this is JP. Good job, Joseph and Nick. I'm very pleased and happy of what I see. I'm looking forward for that final report. I believe it's coming out in March timeframe, correct?
Mm-hmm. Yes.
Yep.
Yes,
That is planned currently. Yep.
Good. I'm looking forward for the next one.
All right, very good, Jennifer, and yeah, we will post those. They're already available. The slides are available on the KMIT, but Walter will make sure that we send the link to all the participants. So with that, again, thank you, Walter. I'm not sure if I did extend my appreciation, but great job of setting this up. So Walter Quintero will be our lead for our Tech Talks, and he'll continue sending the information and announcements of the future Tech Talks. And as I mentioned, April 20th would be the next one. The theme would be robotics across the for nuclear decommissioning applications. So Walter, I leave the last word to you.
No, thank you. Just want to remind everyone that there is a feedback form available at the Tech Talk website, which the link is provided on the chat. There's also on the same page, you can see a link to sign up for our newsletter. So if you want to stay tuned for future newsletters, future news and events from ARC and D&D KMIT, please sign up for our newsletters. Thank you everyone for attending. If you have any questions, follow up on this. You can download the slides from the website. You can email Joe, Connor, or Leo. If you have additional questions, we'll follow up. This event was recorded, and we'll be posting the recording later on the same website, and we'll send a notification email when that is done. That's it.
Well, thank you very much. Thank you everyone for joining us. Have a good rest of the day.
Thank you, guys.
FIU signing off.
Bye-bye. Signing off.